Good afternoon, everyone. So today we are going to start our next part of this unit. Uh, Basically, I'm going to build up the basics of. Good afternoon, Kajal. Good afternoon. So basically, yeah. So as I introduced on the day of introduction, that we are basically going to work upon the ensemble theory. Firstly, we will go or begin with the classical ensemble theory. That's the part of classical statistical mechanics, and I think with that, your Unit 1 or MST 1 syllabus is going to be excuse me cover up. Then after your MST 1, I think we will initiate the quantum stat math part. But that's okay. So today we are going to begin with this second subchapter of Unit 1. That's the elements of ensemble theory, and today I'm going to introduce you to the basics. And but let me tell you, these basics are very critical because in ensemble theory basically there are three different versions. You might be remembering I told this in the beginning also, that we will be talking about micro canonical ensembles, canonical ensembles, and grand canonical ensembles, right? They have their own characteristics that we'll discuss later, but all of them they all begin with the same basics. So that I'm going to talk about today. So if you understood these things or these basics correctly, then you will go through. Otherwise you will struggle throughout this course or maybe later also to differentiate between various ensembles and as such the ensemble theory, right? So feel free to ask the questions during the lecture, or you may message me later after the lecture also. That's always the option you have with you, right? But usually most of you don't ask anyway. So before I begin, if any one of you want to ask any question of last unit previous what we have done, we basically talked about mostly the thermodynamics, right? So I tried to consider a system, and in unit 1 the only system we consider was the ideal gas. Okay, and then for the given ideal gas we talked about various kind of ways to approach that how do we can calculate the number of microstate accessible to the system given a macrostate NVE, right? So we talked about what I would say, or maybe let's it's written here also, that let me show you. Yeah. So okay, yeah. So we had our macro state, which is defined by these extensive parameters: the number of particles in my system, the volume occupied by my system, as well as energy possessed by the system, right? And of course the all the time the number these constraint has to be satisfied, that if ni number of the particle occupying energy level having energy ei, so this must sum to the total energy, right? Where these are the possible energy eigenvalues, you can say I runs over the number of energy states available, and this sum of all the particles occupying all the energy levels that also must sum to this total number of the particles, right? So these equation has to be satisfied. These are the constraint that my microstates has to satisfy. So then what we considered in last chapter, or maybe I would say in last 5 lectures. Actually, there were 6 lectures, but the first lecture was just kind of introduction. So we spent 5 lectures on completing chapter number 1. So now we are starting chapter 2. Then we considered symbolize the number of microstate via this symbol also, where my energy was precisely defined. And then I told you that this is not the case always in a real situation. So if you remember when we calculated the volume of a hypersphere with radius, if you remember, E star square root in maybe lecture number 3, I guess, then we said that okay, let's calculate all the microstates which are basically having energy less than or equal to this energy defined by the macrostate. Okay, then we calculated that number also. If you remember, this was basically a sigma n kind of E star kind of thing, where this sigma is the symbol for number of microstates. It's not the summation. I told you this again and again. Then instead of this, we jump to the more realistic situation where I said, okay, let's in a real situation, instead of defining energy precisely below a fixed value. Instead, better situation would be if we define the energy in an interval delta kind of thing, right? So then we also calculated this number tau for a ideal gas, if you remember. And then once we had the expression for these guys, and then we saw that we can immediately calculate the thermodynamical parameter of all the yeah, pressure, temperature, your chemical potential, uh, your Gibbs free energy, and so on, right? So we saw all those things. These are kind of preliminary, or you can say like just a warm up thing for what we are going to do now ahead in the classical statistical part. And we, by the end of the chapter, we also saw that the entropy expression was derived by considering this had some issues while we were looking at the entropy of mixing, and we looked at very important central issue with the way we calculated the entropy expression, the Gibbs paradox, right? Then I told you that how we can get around that from you can say very preliminary, just excuse me, sorry for this, forgot to put it on vibration. Okay, so then yeah, this we will address again, or maybe get a deeper picture when we'll jump to the quantum stat mech part, right? So this was all, or I'm briefly reviewing. Somebody message, let me see. Okay, so now as we discussed, as because given a fixed macro state, so a large number of microstates are available for a system. Okay, and if you want to have calculations, this is going to, you can like have feeling that what type of or what this number could be. Let me tell you, this is going to be extremely large. Even if you consider 1 mole of gas, right, the number of microstate accessible to a, you can say 1 mole of gas, for example, if it is occupying certain volume at a normal temperature and pressure, the number of microstate is enormously large, right? So you can consider for practical purpose it is infinite actually. Okay, very large number of microstates are there. That I'll give you one example in today's discussion also. So the idea is, so where the system would be, so we discussed something in the beginning, if you remember, I called something a principle of equal a priori probability, right? So what does that mean is, given a macrostate, my system can be in any one of the microstate at a given time. So the system occupying a particular microstate, the probability of that thing is equal for each microstate, right? So there is no biasness or preference if my microstate is fixed, right? So at any time, given time, my system can be any one of them. And as time progress, as time passes, so what system does if there is something evolving, for example, the gas inside your room in where you are sitting, right? Or maybe a liquid or maybe a water inside a glass, all the H2O molecule, maybe some impurity, they are moving here and there. Okay, so what's happening basically? So if I ensure that NVE is fixed or having some definition the way we defined here, right? So then the system is basically switching between one microstate to other, to other, to other. So this is happening all the times, right? And even you can't imagine that at how fast rate this is happening. Okay, so even maybe a system may you can say go through 10 raised to power 20 to 10 raised to power 30 microstate maybe in a fraction of second. Okay, so that's how fast the system is changing, because the number of degree of freedom attached to the system are so enormously large, because system is composed of, as I gave you example, that if you take 1 mole of a sample, it's going to be roughly 10 raised to power 23 number of particles, right? So each particle's degree of freedom, so total number of degrees of freedom are so enormous, its number is so large, that number of microstates are also so large. So system is switching very fastly. For example, out of these 10 raised to power 23 particles, even if one particle changes its states, then microstate is changed, right? Now you just imagine how many particles are there and how many possibilities are there that they are going to switch the microstate. So the change, the system changes from one microstate to other, the number is, this rate at which it is changing is very fast. We are not going to even dare to calculate that. But idea is we can say few things about this, right? So Yeah, this is another observation which I just was talking about. The time spent in each microstate is ridiculously small. Okay, so this is going to be even lower than any known you can say observable time scale. So this is going to be, and we are not going to calculate it, although we can calculate, but that's not the motive here. So yeah, this I already said, the system keeps on switching between various microstates at a very, this is important that you must understand that this change is very fast, extremely fast, right? So do you understand that what system is doing as it is evolving through time? It is basically changing between various microstates. That's what it is doing. Okay. Now, if suppose you decide to measure some property of the system, maybe pressure, temperature, chemical potential, uh, Gibbs free energy, maybe whatever you are interested in. Okay, or maybe ensemble average of something. I'll talk about this term ensemble average. I like, as I did bit earlier, but I'll define this also. Okay, so what you are going to do, right? You are not, or you are not capable to measure the property of that property of the system in a particular microstate, right? Because the moment you are going to measure, the system almost instantaneously is going to switch to another microstate. So whatever you are going to do a particular measurement of some parameter, for example temperature, you put the thermometer inside of the sample, right? So there must be some measurement time. Over that measurement time, so the number of switching between various microstates is enormously large. So what you are going to measure, you are going to measure the average behavior of the system over all those microstates. This is what you are going to measure, and this is what you do actually. You are being scientists, scientific community, we do this always. We just measure the average behavior of the system over a very, very large number of the microstates. Do you get this point or not? First tell me. Just okay sir, yes sir message would be enough. I know many of you don't say anything, but that's your choice. Did you get it? What I'm saying is about the system. Or should I call someone? Okay, Rahul, this is not very hard to understand, but the idea is like why I'm talking about these things. And today is not going to be mathematical. You can see lecture. It's more of conceptual things. It's more of a talk, right? Rather than driving the entropy kind of thing or driving the thermodynamics of the system, given that entropy is there. So we are not going to do that today. Today is bit theoretical and it's quite important and central. Okay. Okay, so I'll try to explain this thing a bit more. So now, so this is my way to represent this thing. Now let's consider this situation just to have a deeper understanding of same thing, whatever I was saying. Suppose a macro state is defined like this, and please mind it, system is switching between various micro states, but macro state is always fixed. Do remember this, macro state is not changing. Okay, so my number of particles are fixed, the volume occupied this is by the my system is fixed, energy being possessed by the system is also fixed, though I can have various situations whether energy is lower than a precise value or it is varying between an interval or it is having a precise value. That's a secondary thing need to be considered, but right now they are being specified, right? So the number of microstates, obviously we are going to talk about this symbol top, the number of microstate accessible given this macrostate. Now what we are saying, suppose we are observing my system from some initial time ti to some final time tf, right? Or you can also say you observe your system from t to t plus dt. That's all equally good, right? Doesn't matter. Then my t initial will be t and t final will be t plus dt, or t final minus t initial will be just dt. So that's equally good. Actually this interval is very small. Okay, so what I try to draw here is that when I observed my system at t initial, it will be in one of the large number of microstates which are accessible to the system, right? So here I just wrote on vertical axis as the micro state label. I don't know, you can put a b c d e f g, but that you will exhaust. You can put the microstate label label, not level, label as 1 2 3 4, maybe billions of microstates may be accessible only to 1 mole of gas. Okay, even I'm saying that number is also very small. Billion is very not too much. Okay, so I'm not concerned about this thing. I want to give you this picture to you. So I have these labels, so it doesn't matter what label you put, 1 2 3 ABC alpha beta, I don't care. Okay, but I'm saying when you were at this time, this is theoretically, experimentally or practically you can't do this. Okay, you can't observe this system's microstate at any given instant, because any instrument you are going to do experiment with, that has its some minimum threshold time or reaction time. Okay, so you are not going to measure the thing instantaneously, but this is purely conceptual thing. Okay, so suppose system was here at this time, it means in this microstate. Then at another instant, after very small time interval, now very means almost zero, the system switched from this microstate to this microstate, so it jumped to another microstate. Okay, then you observed it at another time instant, then system jumped to this microstate. So it's basically jumping between various microstates, right? Or maybe you can actually draw a trajectory like thing also, there is no issue. And this trajectory may not be, you can say, uh yeah, it's just a minute, this is wrong actually, because there are, maybe okay, let it be. Now these are so closely spaced because they are almost infinite number of microstates accessible, and even time is continuous, right? So whatever interval you define, I can take always center of that another point of observation, you can say. So means at this particular moment, another microstate was accessible. System was in at this moment, it was in another. So this is going to do like this. It is going to do this very fastly, right? So suppose you choose to measure a property. Now I will call this as situation number one. This is what system actually doing. Okay. Now this is important. Okay. Try to means direct your focus here. Instead of talking about this situation, I will consider my this same situation from another perspective. Okay, but before introducing this particular thing, let me tell you another something different, right? Suppose you are doing some experiment with coins. You know, you flip a coin, you get head and tail. Yeah, we know this. Okay, I asked you to do some experiment. For example, I give you this situation. Okay, you just flip the coin 6 times, for example, right? Six is one a number I'm just taking random. You can take 6,000 or 6 million, it doesn't matter. So you just flip the coin 6 times and just note down what are the outcomes: head, tail, whatever. So you will give me six numbers, right, as a result of your experiment. That is going to happen. This is the one situation. So it means your same coin. Now see here, your coin is same, but it is in 6 different states at 6 different instants, right? This situation is actually situation number one. If you see your coin, so you can say the whether it is head or tail at different instant is one microstate. So this is same system in different situations, it's behaving like this in various microstates. But now you can perform same experiment with 6 coins flipped simultaneously. That can also be done. Both results are equally good, right? So similarly, instead of observing my system like this, how it evolves over time, what I am going to do, I will consider the copies of my system at all the instants. Okay, what generally referred in the text or literature as mental copies. Okay, then suppose whatever you can say parameter I am interested in measuring, if I measure in this situation number one, that would be called as time average behavior of my system over the time of observation, this much. So I will be observing just time average over this time, suppose this delta t, which is t final minus t initial. So instead of doing this, I can measure the average behavior of same system over all those mental copies, right? One and same thing. And these mental copies or group of these mental copies is what is termed as ensemble, right? So please ask question if you have over here that why so. So very simple example to understand this. This is basically situation number two. So we are not measuring, or you can say we are not measuring the time average, which is basically situation one. but we are measuring the ensemble average now, which is the situation 2. So I gave you the example. This is exactly similar, that you perform experiment, flip single coin 6 times at 6 different instant of time. You measure the head and tail or record the outcomes. Instead, you flip the 6 coins simultaneously at single instant. You can have, so those 6 coins I would call, they are mental copies of each other, and group of those 6 coins I will call as ensemble. Do you understand this or not? So this is what forms the basis of the ensemble theory. Doesn't matter be it micro canonical, macro canonical, or canonical or grand canonical ensemble. All of them base starts from here. So if you understand this much, it's fine. Then if you have question, you can raise now. I'm waiting maybe 10 seconds for your responses. Okay. No. So I'm explaining so nicely. I don't believe. So you are not understanding, or you choose not to respond, but that's your choice. Okay, let's move ahead then. Now, next step, or next, you can say, point would be, okay, everything looks good. So instead of talking about the time average behavior of situation 1, we will be talking about the average behavior of the system in this ensemble in situation 2. So they both are basically equivalent, as I said, in terms of that coin experiment, right? Now, the if we look at, for example, a gas sample, right? And for gas sample, I define a macro state, kind of NVE, right? That how many number of molecules it has, what is the volume it is occupying, and what's the total energy. It's basically related to temperature, if you remember now. So what could be the physical parameter which can define a microstate of the system, right? Now let me try to draw maybe kind of thing. This is suppose a cube. Maybe it doesn't matter whether it is I'm just representing that there is a volume. It's filled with gas, atoms or molecules, doesn't matter actually. This discussion is valid for any system you talk about. And they are, of course, they are moving here and there. They are randomly moving here and there. We saw, I think, you can have this picture is there in your mind, right? This is not something new, I'm telling you. So suppose I just take a snapshot of this dynamical system, right? Suppose that time is t0, right? So what you can say that you can, what we need to define the state of the system at this instant, what do you say? So my question is, what we need to define state of system at this instant? So that's the question mark. Anybody want to answer this, or should I? And by the way, from 28th onward, many of you will be joining the campus physically, those who chose. And the section I will be teaching is basically physical one, right? So maybe those who out of you chose to go online, they will be shifted to other section, and people from other section who chose to come physically on campus, they will come to my class, right? So that will be great actually, so that we can have one-to-one classes. Okay, basically it's very easy answer to this query is that you just tell me the position of first, for example, atom, position of second atom, and similarly position of nth atom. This could be the one definition to define, but that's not enough, right? uh, Particles are in so and so position having so and so. Yeah, Rohit, you are answering really nicely. Yeah, but instead of position or velocities, we are going to define the momentas, right? Because if you remember from our last course, the classical mechanics, the phase space is more favorable kind of you can say space to discuss the trajectory, right? In comparison to configuration space. Yeah, because of those all kind of you can say canonical transformation can happen in a phase space. Okay, so this is enough. So, and you know that if these qi ti's as a function of time, because of course they are changing with the time, these things, right? This usually I will be calling a representative point in phase space. Although we saw the trajectories in phase space also in last course classical mechanics, right? So of course this definition you need to define all these. So this at any given instant t is going to be one of the microstate. So this is the system is in at time t naught. As suppose time t changes from t naught to t1, this set is going to change. So that will be, suppose this was my microstate number 0. When it will change, time will change from t0 to t1, my microstate will also change from suppose label 0 to label 1. So now I will have another microstate, right? So it means this is going to be a good candidate, the phase space. And if we see the trajectory, or you can say these representative points in phase space, every such point in phase space as time evolve is basically going to be a one accessible microstate. Actually now you can see, because there is no discreteness is involved in q's and p's, they can in principle have any you can say real values. So I have infinite number of microstates. Okay, okay. So let me see what I have written about this. Yeah, this is same whatever I discussed with you. If I'm having a defined macro state, then I need, yeah. Can you understand that if there are n particles, why there will be 3n position coordinates? For example, if I only have two particles, for example, I think this is your master students, right? This I should not explain, but I'm explaining. So two particles, to define their position, you need six coordinates: x1, y1, z1. These are the three coordinates of first particle. Similarly, x2, y2, and z2. These are the three coordinates, position coordinates of particle number 2. Similarly, if I have n particles, so I will require 3n position coordinate. Similarly, 3n momenta coordinate. So basically I am talking about the point which is, I'm calling this representative point in a 6n dimensional space, which I am calling, or we all know by now, that if we are talking about the positions and momenta, so then we are basically dealing with phase space. We learned about so many various spaces like a configuration space, phase space, Minkowski space, right? So we heard about these things, and we learned, and we know how to deal with them. And of course the equation of motion for these qi's and pi's, the representative points, are nothing but your Hamilton's equation of motion. And where this h, if you remember from your last course, which is not too long ago, we recently studied this. So this is nothing but the Hamiltonian of my system, right? And yeah, if we are talking about, you can say time independent Hamiltonian, then Hamiltonian also represent my total energy of the system. This is one special case I'll talk about on next page. Okay, looks good. Okay, so now yeah, this is what I said. Basically the representative point is basically equivalent to microstates, right? So as a system progress, or yours, for example, the example of that gaseous matter inside a cubical box, that's one example. But in general, as time progress, so these qi pi are going to change with respect to time, dictated by Hamilton's equation of motion. And at each instant, these qi pi are going to have values, are going to have this is basically a point in 6n dimensional space, because 6n number of parameter need to be defined to define a microstate. So, and of course this evolves with time as time passes. And equation 1 is going to govern. Equation 1 is nothing but Hamilton's equation of motion. This is going to govern how this is going to change with time, right? And there is one important observation here. This is going to be important. Okay, the values qi pi are limited. Okay, for example, I had box over there, right? So there was some box. So suppose if I define my xyz like this, my x axis, y axis, z axis, and if some particle is somewhere here, of course it will have a position vector with respect to origin, then it will have its x coordinate, y coordinate, as well as z coordinate, right? But it xyz or the qi is limited by the volume of this box. Do you agree? So it means qi is going to be limited as my volume dictates. Similarly, we remember, if you remember, if zero potential is there, the Hamiltonian is p square by 2m kind of thing, and if it is independent of time, then Hamiltonian looks like this, and this goes to energy, if you remember, right? So if my macro state decides the energy, even my momentum has some limits, right? It means my these QIs and PIs has certain bounds on them corresponding to what type of macro state they are representing, right? So volume and energy are going to limit the values qi pi can take, and they are of course dictated by equations of motion by Hamilton. So it means the full phase space volume is not accessible, or the microstates which are you can say accessible to the system are not occupying the full phase space volume. If energy is fixed, like I fix out of the two parameters energy and volume, if I fix the energy, then it is a hypersurface in a phase space. Okay, and this is going to be something like this. If your energy is defined by Hamiltonian, and the Hamiltonian doesn't explicitly depend upon time, then energy Hamiltonian represents the energy eigenfunction. And if you remember, this we studied in classical mechanics. And if we talk about this kind of thing, that your energy is lower than some fixed value, then it's basically a hypersphere in phase space. And if your energy is varying between, basically why I'm referring to these are the cases correspond to calculation where we calculated these three guys. Okay, the number of microstates like this. So these different scenarios are correspond to this. So if energy is varying between this energy interval, then in hyper you can say in phase space, I will be talking about a hyper shell where my representative points or allowed accessible microstates will be lying, right? So these are various you can say situations we can come across. Okay, any question till now, if you want to ask? Okay, if not, then let's move ahead. A couple of things I want to say more, then I think we'll continue with this, you can say foundation next time. And please do read. These are just couple of pages in your textbook. Okay, don't leave it to next time or next time. Otherwise, you are going to lose on it. Let me ensure you this. Okay, so now I'm saying is, suppose you are considering a ensemble. Ensemble, now in mind you should be clear that these are just mental copy of same system in various microstate, but we are considering all of them at same instant. So that's the meaning of ensemble. Each element of ensemble is representing basically system in different microstate. But in reality, you know, system can be only in one of the microstate at a time. Okay, that's the real picture. But we are considering the ensemble picture where we just took all the you can say possible microstate in which system can be in, and we just consider the group of that mental copies, and we are calling that as ensemble. That's what I'm referring to as ensemble version of my system. Okay, and at this time, the members of my ensemble will be in all possible microstate. All possible means the microstates which are dictated by macrostate. Okay, as I told you on last page, only a part of my phase space will be available as per definition of the macrostate, which may be a hypersurface, a hyper sphere, or a hypershell kind of thing. Okay, hypershell you would see is the most appropriate thing when we are going to do the actual calculation. And this we saw in the last chapter also, that we were the more realistic situation is the energy interval instead of precisely defining a particular energy, right? And corresponding to that allowed region in, you can say, phase space, I will be having a representative point. Each ensemble element is going to represent one point in the phase space, right? That's what the definition of representative point is. But because we are considering simultaneously many microstates, so there will be very large number of representative point corresponding to each ensemble member in the hyperspace of allowed region as per dictated by the macrostate definition. Okay, so yeah, so that's what I'm saying here. And in order to further, you can say, understand this, and you need to listen this video and read your text as well, maybe 5 to 10 times at least, to understand or to absorb this. Okay, so just to like explore or exploit this feature which we built up, we need to define a density function which will be looking something like this, right? And why I'm calling a swarm of representative points? Swarm, I think it's a term which you can think, you might have seen birds flying in groups, right? Maybe when this spring season comes, they flow in, they fly in sync with each other as a whole. This group like fly in sky. So this swarm is basically term taken from that scenario. So these representative points which each ensemble element is representing in a phase space. So you have very large number of such representative points. So all those points, they have been termed as swarm of representative points, because this swarm is basically representing the ensemble in phase space. Okay, so we defined something called density of these points in phase space. This has certain particular characteristic. I'll quickly discuss this and I'll review this in next lecture also, and that will be, I think, should be enough for today, because this is theoretical and you people need time to absorb this. Okay, so now suppose I have defined my this density. What does this mean? Okay, so let me, because in 3D I can't draw a 6 dimensional space. Suppose I am having, this is my 6n dimensional space. Okay, although this is 3D, but just imagine, nothing wrong in imagining. So I'm considering very small volume in this phase space. Volume of this space will be, what's the volume of, by the way, normal space? It's dx, dy, dz. This is how you write in 3D, right? But we are representing 6 dimensional. So, or this is also equivalent to d cube q, if I'm representing q as x, y, z. So three elements are there, but I'm representing phase space. So it will be d3 q, d3 p. But because I am representing n particles, so it will be d3n, d3n. So this will be the volume element in phase space of 6n-dimensional system, right? So this is the point, or this is the volume around a representative point qp. So the density of, or you can say the number of microstate in this small volume, which you can call as dv also, around representative point qp at time t. Important point is that time is also involved here. Okay, is given by this. It's so easy. This is how the density function is defined. Okay, this is something called, what will be the mass of a small volume dv if the material density is rho. So you will write like this, right? Dm is rho dv. So because this rho is representing in present scenario is the representative point density. So that's why if we are interested in calculating the number of representative points, so we will multiply the representative point density by the volume of that element in space. So this is one thing. And also, as I said in the beginning, that instead of time average, we are now going to measure the ensemble averages. So suppose you are measuring some function f, which is function of these uh, canonical, you can say, coordinates, the position and momenta. So the ensemble average, this ensemble, although we are still in classical mechanics, but the classical statmet, but we are using this ensemble, which is more familiar in quantum statmech or quantum mechanics, I would say. But that's not much wrong. This is unanimously used for average, representing averages, right? So this goes as integral of this function multiplied, this rho is stuck there. I did not did not write the functionality here, right? But that's understood. Multiply with this volume and then just renormalize it with respect to integral. And of course this integral is over whole of the phase space, but you know only allowed region of phase space are you can say accessible to the system. So this integral will only contribute in the region where this rho is non-zero. Okay, all other everywhere else it is going to be zero, but by definition this integral is over whole phase space. Do remember this, right? So the last thing I would say, I know a couple of minutes above the time, but I'll say this last thing. If this row doesn't depend upon time, this row, the density of representative points, then my ensemble average will also be independent of time. Okay, and if this row doesn't explicitly depend upon time, that means curly row by curly t is zero, then I would call that ensemble as a stationary ensemble. Okay, I will begin from this point next time onward. I think that's all from my side. And if you have any questions, then you may ask or type in, else you are good to go. Thank you.